Hello everyone, this is Vipul Purohit and I welcome you to my YouTube channel. My dear friends, in this particular video I am going to consider the part 2 of applied electrochemistry. I hope you have gone through part 1. If you haven't gone through, no worries. I will put up the link of that part 1 video in the description box. So here we start with part 2. In part 2, we begin with the electrolyte concentration scale. The first we are going to start with is without transference, and that's going to be reversible to cation. So the pattern is going to remain the same as I discussed in part 1. So let's consider a cell whereby we have Ag plus in contact with AgNO3. In the same electrode we have once again, only differences in terms of the activity. The electrolytes are going to be the same but having different concentrations. So the left hand side is having an activity A1 and the right hand side is having an activity that is A2. Next we go for the cell reactions, the half cell reactions, that is the left hand side as well as the right hand side. So in the left hand side, silver is going to lose an electron and thereby it undergoes oxidation, and that is forming a silver ion. Now this silver ion is going to accept the electron and thereby it is going to give you silver in the atomic form. So atomic silver is going to be deposited. And when you go for the net cell reaction, you get the silver ions on both the sides, but the activity of both of them is different. The left hand side is A2 and the right hand side is A1. Now the next thing is we go for the Nernst equation. So E cell is equal to E naught cell minus 2.303 RT upon NF into log of, as we know, it's going to be product upon reactance, so it is going to be A1 upon A2. Next thing is it's only one electron is being involved, so N is equal to 1. You also know very well that the composition of the electrode and the electrolyte is same, and therefore the E naught cell is going to be considered as 0. So the Nernst equation reduces to E cell is equal to minus of 2.303 RT upon F into log of A1 upon A2. And then we don't want the negative sign, so as you all know that what we do is we do the denominator getting combined to numerator and vice versa. So we have E cell is equal to 2.303 RT upon F log of A2 upon A1. Now, my dear friends, at 298 Kelvin, 2.303 RT upon F has a value of 0.05916, or that is we call it as 0.0592 into log of A2 upon A1. So now when we talk about A, it stands for activity. Now this activity is also being related to activity coefficient by the expression that is A is equal to m gamma, where m is the molality and gamma is the activity coefficient. So substituting that relationship as A is equal to m gamma, we have equation that is 0.0592 into log of m2 into gamma 2 upon m1 into gamma 1. Alright, so for spontaneity of the reaction, as we all know that the numerator should be greater than the denominator, so the fraction is going to be greater than 1. So we have A2 greater than A1, or in other words we say M2 gamma 2 is greater than M1 gamma 1. So this is, my dear friends, with respect to the reversible to cation, where the cation which is under consideration is a silver ion. Now the next part we go into, and that is reversible to the anion. Now here what we do is we are going to consider an electrolyte that is HCl. It's going to be the same as we had in the previous case, that is AgCl, but that AgCl was reversible to the cation, that is Ag plus. Now here we are taking AgCl, all right, but at the same time we are going to take HCl as well. So here what happens is it is going to be reversible to the anion, that is Cl minus. Alright, that's the only difference, that's it. So here we go, consider a cell that is AgCl, HCl, and then we have a salt bridge, and then we have got HCl, AgCl and Ag. Only difference is the activities of HCl A1 on the left hand side and A2 on the right hand side. So as usual, now the left hand side we write the reaction as silver is being treated with a chloride ion, that is the chloride ion is coming from HCl, and that is giving AgCl with the loss of an electron. That electron is accepted by the AgCl, that gives you Ag, that is silver in the atomic form or neutral form, and it gives Cl minus, and that Cl minus is going to be from A2. So cancelling the common ions and cancelling the electrons, what we have finally, the net cell reaction is Cl minus on both the sides, but only difference is on the left hand side we have is A1 and on the right hand side we have A2. Now as usual we follow the Nernst equation, so E naught cell minus 2.303 RT upon NF log of A2 upon A1. Alright, now n is equal to 1 over here itself, so n is going to be ignored. So, and also the electrode and the electrolyte are same, so E naught cell is equal to 0. So we have minus of 2.303 RT upon F into log of A2 upon A1. Now, as usual, we don't want the negative sign, so we have 2.303 RT upon F into log of A1 upon A2. Now at 298 Kelvin, the value you know very well, that is 0.0592 into log of A1 upon A2. And hence we also say, as because A is M gamma, so M1 gamma 1 upon M2 gamma 2. So you can understand the difference, my dear friends. With respect to reversible to the cation, we had M2 gamma 2 upon M1 gamma 1, and here it is M1 gamma 1 upon M2 gamma 2. And for spontaneity, the rule remains the same. We want E cell to be positive, so the fraction, the ratio should be greater than 1. So A1 upon A2 will be greater than 1 only when A1 is greater than A2. Alright, so I hope this part is very clear to you, and that is reversible to an ion. Now we go into the next part, and that is, my dear friends, is electrolyte concentration cell with transference. Now here when we talk about with transference, so obviously there is a transfer of mass taking place from one cell to another, and that's very obvious that we don't have a salt bridge now. Okay, so we have a reversible to cation, so PT H2, then HCl. Once again we take HCl with a different concentration, and then H2 and PT. So left hand side the concentration, the activity is A1, and the right hand side we have A2. Now here in this case we are going to consider the transferred numbers. Yes, because there is no salt bridge, so obviously there is going to be a transfer of mass. The speed, the mobilities are going to be different because the concentration is going to be different, and hence we need to consider the mobility in terms of transferred number. So T plus is the transferred number of H plus, and T minus is the transferred number of Cl minus. So now, as usual, the left hand side electrode, what we do is half mole of the hydrogen gas is going to undergo oxidation, resulting in the formation of a proton, that is H plus ion, the concentration of which is A1. This is of H plus is of HCl A1. Now the next step, what happens is the H plus of HCl with the activity of A2 is accepting an electron, and as a result of which half a mole of hydrogen gas is evolved. So when you go for a net cell reaction, summation of the two reactions, cancelling the common ions, we have H plus ions on both the sides. Only difference is the concentration, and that is on the left hand side we have A2, and on the right hand side we have A1. Now what happens is we need to consider an electron which is going to be flowing from a left hand electron to a right hand electron. Alright, and to balance this, what is going to happen is the T minus gram of Cl minus from the right hand side will go into the left hand side. Alright, because the electron is also negative, Cl minus is also negative, so in order to balance it, it will go in the opposite directions. Now if T minus or Cl minus is going to go from right to left, so it's very obvious H plus, that is the T plus gram, that is T plus is the transferred number of H plus, will be flowing from left hand to the right hand. Alright, because the direction changes, because the sign changes. So keeping this in mind, I once again repeat, my dear friends, the electron will move from the left hand electrode to a right hand electrode. To balance this, the T minus of Cl minus, okay, will move from right to left, and as a result of which, to maintain the electrical neutrality, the T plus of H plus will go from left to right. And hence the equation is T minus of Cl minus A2 will give T minus of Cl minus A1, because we are going from right to left. So it is A2 to A1. Now for H plus ions it will be opposite. It will go from A1 to A2. So T plus H plus A1 gives T plus H plus A2. Also, my dear friends, please remember the total transferred number is always equal to unity. Okay, so T plus plus T minus is equal to 1. So therefore we have T plus will be equal to 1 minus of T minus. So substituting in that equation with respect to H plus, okay, we have, instead of T plus we will write down 1 minus of T minus H plus into A1, and that is going to give 1 minus of T minus of H plus A2. Okay, now when you consider the total cell reaction, then what are we going to do is we are going to add reaction 1, 2 and 3. So have a look at this very carefully. When we add all these reactions 1, 2 and 3, so as a result of which the final reaction, you can just go very slowly. Okay, I'll give you time to go through those 3 steps. I've also cancelled the common ions, and after cancelling the common ions you can check T minus of H plus A2 plus T minus of Cl minus A2 gives T minus of H plus A1 plus T minus of Cl minus A1. So as a result of which we have on the left hand side T minus of HCl A2 giving T minus of HCl A1. Okay, have a good look at all the 3 steps. Alright, we are opening the brackets. The negative part we are shifting the directions so that the similar concentration species, similar activity species come together, and when H plus and Cl minus of similar concentration comes together, I can write it down as HCl. Alright, so I hope you have understood this. We move to the next part now. Next part is very simple. Next equation. So we have E cell is equal to E naught cell minus 2.303 RT upon NF into log of A1 upon A2. So 2.303 RT upon F log of, this time we have A1 upon A2, and that is the T minus is going to be the coefficient, so it goes into the power. So we have minus of 2.303 RT upon F log of A2 upon A1 T minus. Alright, so that means we have T minus of 2.303 RT upon F into log of A2 upon A1, because that T minus was in the power, so we have just brought it on the other side. Now HCl is a univalent electrolyte, okay, because it is having one H plus and one Cl minus. So for a univalent electrolyte, we have an expression saying that activity is equal to the molality into the activity coefficient raised to 2. So A2 is equal to M2 gamma 2 squared, and A1 will be M1 gamma 1 squared. So substituting all these things, what we have is E cell is equal to T minus of 2.303 RT upon F log of M2 gamma 2 upon M1 gamma 1 the whole square. So therefore we have 2 into T minus 0.0592, because as you know that at 298 Kelvin the entire value of 2.303 RT upon F comes out to be 0.0592 into log of M2 gamma 2 upon M1 gamma 1, because previously it was raised to 2. So applying the log rules, so that 2 comes before T minus, so we have 2T minus. So this is, my dear friends, the entire part about reversible 2-cation, and that is without the salt bridge, so it is with transference. Now once, my dear friends, if you have understood this, reversible to anion is very easy, and that is what we do this time is we are going to take the same cell as we have taken before also, so it becomes easier for you to remember. So we have Ag, AgCl, HCl, HCl, AgCl and Ag, all of them are in direct contact with each other. Now here the electrolyte which we are going to take is HCl, but having different concentrations, that is A1 and A2. We have the first half cell reaction, that is silver in the metallic form, in the neutral form, will react with the chloride ion, resulting in the formation of AgCl with the loss of an electron. Now this electron is going to be accepted by AgCl, okay, and reacts with chloride ion and gives you Ag plus Cl. In the activity form is A2. So if you cancel the common ions, what we have is Cl minus of A1 giving Cl minus of A2. So chloride ions on both the sides, but with different concentrations. Now, as I said earlier, electron is going to go from the left to the right. To balance this, T minus terms of Cl minus will go from right to left, and therefore the H plus will go from the left to right. Alright, the same thing which I had explained to you before as well. And T plus plus T minus is equal to 1. So now we have T minus is equal to 1 minus of T plus. Okay, because this ion, remember, it's reversible to the anion. So we are going to express it in terms of the transport number of the anion. So it is T minus is equal to 1 minus of T plus. And then accordingly we can begin with T minus of Cl minus of A2 giving you T minus of Cl minus of A1. So instead of T minus, we write it down as 1 minus of T plus. Okay, and then similarly, when you talk about H plus, we are going to keep it the same, that is T plus H plus A1 giving you T plus H plus A2. This is equation number 3. And then when we add all the equations, that is equation number 1, 2, and 3, what we get is this. Okay, you can have a very close look of this. I'll give you some time. You can go through this very slowly. Yeah, cancelling the common ions, also bringing the concentrations together. So finally what we have is T plus of HCl A1 gives you T plus of HCl A2, and then you apply last equation. So we have E cell is equal to E naught cell minus of 2.303 RT upon NF log of A2 upon A1, and which is raised to T plus because that's going to be the coefficient. Now here N is considered as 1, so that's ignored, and we have A2 upon A1 T plus. We put it in front, that is in the beginning of 2.303 RT upon A, but remember there is a negative sign. So we want to remove that negative sign. So that means we make it as A1 upon A2 instead of A2 upon A1. So finally we have E cell is equal to T plus 2.303 RT upon F log of A1 upon A2. Now here the electrolyte is once again HCl, so it's a univalent electrolyte. So A1 will be equal to M1 gamma 1 the whole square, and A2 is equal to M2 gamma 2 the whole square. So we substitute that. So we have log of M1 gamma 1 upon M2 gamma 2 the whole square, and then applying the log rule, that 2 which is in the power will come just before T plus. So we get the final expression saying that E cell is equal to T plus 2.303 RT upon F log of M1 gamma 1 upon M2 gamma 2, or we can also write it down as 2.303 RT upon F as 0.0592. Okay, this is what we get, and this is for reversible to the anion. Only thing is that I want you all to very clearly look through the equation that we get after adding 1, 2, and 3. Okay, rest everything is very simple. All right, so this is, my dear friends, about all the different types of cells which we talked about. Okay, the chemical cell, the concentration cell, then the electrode cell, then the electrolyte cell, then we talk about with transference, without transference, and then we talk about reversible to cation as well as anion. Now we go into the next few terms. Okay, I just quickly give you a summary of that, and that is about polarization of electrode. Now the difference between the operating potential of the electrode and its equilibrium potential, okay, that is being called as polarization of an electrode. Okay, there is an operating potential always which is there. Okay, an equilibrium potential, that means that when it comes to a balanced state. Okay, so the difference between the two is called as polarization of electrode. We go into the next part, and that is decomposition potential. It is the minimum potential which must be applied between the electrodes which are being immersed in an electrolyte solution so as to bring about continuous decomposition of the electrolyte by the process of electrolysis. Okay, now see, whenever we consider an electrolyte, we have to decompose it. Decomposition of electrolyte generally gives you ions, okay, because they have an ability to conduct electricity. So the minimum potential which is required so that the electrolyte which is going to be considered as a cell where the electrode is immersed into it, so there is going to be a continuous decomposition taking place by the process of electrolysis. This minimum potential which has to be applied, and that is called as a decomposition potential. Next term we go for is overvoltage, which is indicated by means of eta. It is the difference in the theoretical value of the potential at which the gas is actually released. Okay, theoretically we just do the calculations, and whatever the potential that is being required at which the gas is actually released, and the reversible potential of the electrode. Okay, there is going to be a difference between the two, and that difference is called as overvoltage. Now here obviously when you talk about overvoltage, we talk about gas. And when we talk about the simplest gas, that is hydrogen, so that is called as a hydrogen overvoltage. So how to define hydrogen overvoltage is where we also talk about with respect to Taffel's theory, because Tafel was the one who has proposed this theory of hydrogen overvoltage. So it is the difference in the theoretical value, okay, of the potential at which the hydrogen gas is actually released and the reversible potential of the electrode. This is called as a hydrogen overvoltage. Now there are various factors on which it will depend upon. Its value depends on the nature of the cathode and the surface area. It also depends upon the concentration of the hydrogen, okay, overvoltage, which is, now when you consider the mechanism of the overvoltage, there are following steps involved in this. First one is, the first step is the H plus ions, my dear friends, are in the bulk. So the transfer of the H plus ions from the bulk means from inside of the electrode, and that goes to the surface of the electrode. That's step number one. Next one is this H plus ions will lose the charge by accepting an electron. So discharge of the H plus ions is going to take place at the electrode surface. Next thing is, when the H plus ions undergoes discharge, it will be conveyed to hydrogen atom. And there will be many H plus ions going towards the electrode surface, so obviously there will be many hydrogen atoms which are going to be accumulated. So accumulation of the hydrogen atom on the surface of the electrode. These hydrogen atoms, because they are very close to each other, they will form a bond, resulting in the formation of a hydrogen gas. So in the fourth step, there will be evolution of a hydrogen gas from the surface of the electrode. So these are the four steps or the mechanism involved. Now, Tafel postulated a hypothetical expression representing hydrogen overvoltage, and that was eta is equal to A plus B into log I, where A and B are constant and I is going to be the current density. Now, when you consider this expression, this is similar to Y is equal to mx plus C. So where Y is eta, okay, and X is going to be log I. So when we plot a graph of eta against log I get a straight line with an intercept. That intercept is going to be A. Now it is plus B log I, where plus B is considered as a slope, and because it is a positive slope, therefore the line is going to be an increasing line. So the slope is going to be B. Okay, the intercept is going to be A. So hence the constants can be determined, the values of which can be determined by plotting the graph. Alright, so that is what is the concept of Tafel's theory of hydrogen overvoltage. We now move on to the next point, and that is about what are the factors affecting the hydrogen overvoltage. First, of course, is the current density. Generally, it is being observed that it increases, the overvoltage, the eta value increases with the increase in the current density. So it is directly proportional. That's point number one. pH. Strong acid and strong base contains a higher concentration of either H plus ions or OH minus ions, and that's going to affect the magnitude of eta. Next is presence of impurities. The magnitude of eta depends on the concentration and the nature of the impurities present at the surface of the cathode. How much amount of impurities and which particular impurities are present. These are the two phenomenal factors which affects the value of eta. Next is temperature. Now since this is going to be a very slow process, so the value of eta will decrease with the increasing temperature. Okay, so if the process had been fast, obviously it would have been directly proportional, but now this is a slow process. Why slow process? Because it involves 4 steps. Greater the number of steps, slower is the process, and therefore the eta value and the temperature are inversely proportional. Next we have is pressure. At high pressure, the value of eta is going to be not significantly affected. It remains almost a constant, but then at low pressure, the value of which changes rapidly. And finally, the surface of the electrode. The magnitude of eta depends on the nature of the surface and the surface area. Generally, its value is high for a smooth surface as compared to that of a rough or an uneven surface. So, these are the various factors which are affecting the hydrogen overvoltage. So current density, then pH, presence of impurities, temperature, pressure, and surface. These are the 6 points that you have to remember. You can remember any 5 because generally the question is asked for 5 marks. So you can remember any 5 of these factors. So this is, my dear friends, in a nutshell, I have discussed about applied electrochemistry. All right, and I hope you have understood this. You got a little bit of a confidence with respect to the questions asked on this. So thank you very much and all the very best for your examination. Bye bye.